Welcome back to part 2 of the capacitors and RC circuits lab. You'll see we have the same equipment that we used in part 1, but we're going to change things up a little bit and use, in fact, the built-in resistor and the built-in capacitor for taking some measurements. The primary reason for doing so is that a light bulb, even though you can use it as a resistor, does not have a constant amount of resistance, whereas these carbon resistors that are built into the board do. So I'm going to get rid of the light bulb in my circuit and wire instead in the 100 kilo ohm resistor. So if I move my green wire over to one end of that, and the other one that was in the bulb socket, I am going to move to the other end of that 100 kilo ohm resistor. Right next door is my 10 microfarad capacitor. So instead of using my external capacitor, I'll go ahead and disconnect that wire and wire that into one end of the capacitor, and the other wire off my external capacitor I'm going to wire into, looks like this is pin 21, and then that goes back to the negative part of my battery. So I have the same basic circuit, and the circuit diagram would look identical, but instead of using the light bulb and the external capacitor, I'm using the built-in 100 kilo ohm resistor and the built-in 10 microfarad capacitor. Other than that, the details of this experiment are the same, but we're also going to be using Logger Pro to capture the voltage across the capacitor when we do this experiment. So I've got a differential voltage probe that connects to my LabQuest, and that connects to Logger Pro, and if this is all working correctly, you can see my Logger Pro screen on one of the screens here within the Panopto recording. I'm going to take my positive lead on my voltmeter and connect it to the side of the capacitor that's closer to the positive end of the battery, and see if I can get it to stay there. Good. And then I'm going to take the negative lead of my voltmeter and see if I have better luck. All right. You going to stay there? No? There we go. All right, and then I see that Logger Pro is already reading a voltage for me, but it's not 0, and I expect this capacitor to be fully discharged in this orientation, so I'm going to go ahead and 0 my potential meter, and that should set the potential to about 0, which it does. All right, we should be ready to collect some data right here. So if I hit collect on this data, and I'm measuring the potential across the capacitor, it's going to 0, and then if I flip the switch, it is still 0. I see why. All right, let's give the 3 volt power and then flip the switch, and there we go. The potential difference is increasing as a function of time when I'm doing this charging. All right, but I would actually like to start taking data when the voltage starts increasing, because if I use Logger Pro to fit a mathematical model onto this and it's able to fit this curve, it's going to keep going way down below the x-axis and give me a model which at least one of the constants in isn't going to make any physical sense. So in order to facilitate that, we do something called turning on triggering. So in the data collection menu on Logger Pro, there's a triggering tab, and I'm going to turn triggering on, and I would like this to start collecting data when my potential increases across, and I don't want to quite choose 0 since I may not get right exactly at 0. I'm going to put in 0.01 volts. And we'll go there. I'm also going to look at this data collection rate. You can really collect at whatever rate you want to. Let's go ahead and collect 100 samples per second. See if it lets us do that. All right. So I'm going to flip the charging switch down to the discharge position and watch Logger Pro. It's recording the potential in the lower corner there, and that potential is dropping off, and it should get back to 0 pretty quickly. It may never hit exactly 0, but it's below my threshold for when I've told the computer to start data collection. So I'm going to go ahead and tell the computer to start collecting data. And notice nothing happens because I haven't met that triggering point. But when I flip this into the charging configuration, it starts taking some data and nicely, pretty much right there at 0 volts at time 0. All right, it looks like it was set to collect data for about 18 seconds. There's nothing magical about that, but that will do. So I'm going to go ahead and do a couple of things. Shrink this graph so it doesn't take up as much of my screen. And perhaps widen my data collection window because I'm going to take another set of data here shortly. But that takes us through step 7 in the lab handout. And step 8 says once the data is collected, use the analysis tools to find a mathematical model that fits this data. I'm going to skip over that step for now, record a separate video where I talk about finding that model and writing that model in the appropriate format. But if that's something you're familiar with, you certainly can pause the video and do that piece right now. All right, so 9 says to repeat the following set of steps to figure out the mathematical model for a discharging capacitor. Here you'll want to adjust the triggering to begin collection when voltage decreases past the value. Well, you'll notice right now the voltage across that capacitor is 2.915 volts. So if I go to my, well, first of all, I'm going to go to my experiment menu and tell it to store this latest run so that I keep that set of data. And then I'm going to go to my data collection and change my triggering to trigger now when it decreases across, and let's go just straight 2.9 volts. And now I should be able to make this other graph. So I'm going to, back in here, start data collection again. But when I start data collection again, my triggering point hasn't been met because the voltage is remaining above 2.9 volts. If we flip this to the downward orientation, we'll notice that the potential drops and it produces essentially a mirror image graph of what we got for the charging graph. Completely up to you, but I kind of like 2 different experiments to be on different graphs, so I'm going to put a new graph here and note that that one actually shows me the potential during the discharging part of the cycle. If I click on potential on the first graph, I can deselect the one from the latest run so that I just have the potential from the beginning run. And if I auto scale that graph, they're going to look pretty similar to each other in shape, but just kind of, again, those mirror image graphs of one another. One is for the charging cycle, one is for the discharging cycle. And this data set is saved and available through the link on Blackboard. So you can download this data set in Logger Pro and do the analysis parts of that experiment. So I'm going to pause the video right here, save this file, and then come back briefly to talk about the questions that are talked about in number 11. All right, so I've saved that data set, and again, I have my charging and discharging graphs within Logger Pro. What happens if we change the resistance in this circuit? Well, I can go from 100 kiloohms of resistance to 47 kiloohms, a little less than half, by just moving those clips over to the side. And now I have the same circuit, but now I have about half the amount of resistance in there as I did before. So I'm going to just compare things on the discharging graph because it's easier than readjusting the triggering all the time. I'm going to go ahead and flip my switch up and let the potential difference across the capacitor increase, which it has done now. And then I'm going to collect that data, wait for that trigger, flip down to discharging. And you'll see we get the same basic behavior. The potential decreases as a function of time, but it decreases at a faster rate than it did when there was 100 kiloohms of resistance in there. With this smaller amount of resistance, the capacitor both charges and discharges more rapidly. I'll go ahead and store that set on that graph and change things up one more time to include two resistors. And I'll put the 100 and the 47 in series with one another, so that will make a larger resistor than either of the previous two experiments. And we will again flip this up to charge the capacitor up to its full potential, just north of 2.9 volts. And when we get there, I'm going to go ahead and hit collect. It's going to, whoop, I waited too soon. Let's try that one again. All right. There we go. All right, we're above there. So I'm going to flip down and set the trigger and begin the discharge. And so you'll notice in this case, with a greater amount of resistance in that circuit, again, same basic behavior. The potential decreases with time. I get a nice curve there, but it takes longer to discharge or charge when you have more resistance in that loop. So this is where I'm going to leave off with this particular video and go ahead and make a third video for those of you who want some guidance on making the mathematical models that are a part of this experiment.